Today we'll be looking at quantum computing now and what it will look like in the not-too-distant future. If you're new to this channel, welcome. This is Mr. Singularity, where we explore the scientific and technological breakthroughs shaping the future as we know it. 50 years ago, smartphones must have been the ultimate computing wizardry. Much as classic computers were almost incomprehensible to previous generations, we are now faced with the birth of a radically new form of computation, something so mysterious that it may be magic: quantum computing. If the term quantum is what makes your mind spin, you're not alone. This very thin, very cold, very sensitive, and very strange universe may sound like an impossible system to create a commercial computer on. But that's just what IBM, Google, Rigetti Computing, and other businesses are working towards. Recently at the Consumer Electronics Show, IBM Q, a pioneering industry effort to introduce quantum computers from laboratories to the real world, unveiled System 1, a sparkling, fragile, and chandelier-like machine that is now the first integrated universal quantum computing system for commercial use, available for everyone to play with. You've already learned about the promise of quantum computers. The properties of quantum mechanics blasts up massively parallel computational schemes that are likely to offer enormous jumps in computing power, theoretically outstripping any transistor-based supercomputers that we might come up with today and tomorrow. It will revolutionize chemistry, pharmaceuticals, materials science, and machine learning. But what makes quantum computers so powerful? To investigate this enigmatic area, I talked briefly with Jeff Welser, Vice President and Lab Director at IBM Research, Almaden, for his experience in potentially disruptive technologies. You will locate the interview at the end of this post. So what the qubits? Now, the basics of how quantum computers work, and it certainly helps if you keep classic computers in mind. The key to the prowess of quantum computers is that they control qubits. All the classical computing processes, texts, picture, videos, and so on, rely on large strings of zeros and ones or bits. At its root, a bit reflects one state or another, such as whether the bulb is on or off, or whether or not the electrical circuit is connected. In modern computers, a bit is normally represented by an electrical voltage or a current pulse. Quantum computers, on the other hand, depend on qubits. Like binary bits, qubits form the foundation of computation, with one major difference. Qubits are usually superconducting electrons or other forms of subatomic particles. Unsurprisingly, handling qubits is a major science and engineering task. For example, IBM depends on several layers of superconducting circuits that are sequestered in a stable environment and cooled stepwise to temperatures that are colder than deep space, near absolute zero. Since qubits exist in the quantum world, they have certain wild quantum properties. The world of entanglement and intrusion. If a bit is a coin that is either heads, 0, or tails, 1, qubits are a flipping coin. In a sense, they are heads or tails concurrently, with each state having a different probability. Scientists use calibrated microwave pulses to overlay the qubits. Other wavelengths and duration of these pulses will overturn the qubits in a slightly different condition, but still in superposition. Because of the overlay, a single qubit will represent much more information than a binary bit. This is partially how, provided the initial feedback, raw forced qubits will concurrently produce a wide variety of possible outcomes. The final response is only possible when the scientists calculate the qubits, also using microwave signals, which cause them to collapse into a binary state. Science also have to run a problem several times in order to double-check the solution. Entanglement is all the more mind-blowing. Applying microwave pulses between pairs of qubits will entangle them in such a way that they both remain in the same quantum state. This helps physicists to control pairs of entangled qubits by merely adjusting the state of one of them, even though they are physically separated by a long distance, hence spooky action at a distance. Due to the predictive nature of the entanglement, adding qubits explodes the computational power of a quantum machine exponentially. Interference is a final property that produces quantum algorithms. It helps to imagine moving waves. Sometimes they boost each other up, constructive. Sometimes they cancel each other out, destructive. To put it plainly, using interference helps scientists to monitor states to intensify the form of signals to correct answers and to cancel those that lead to incorrect answers. How do you set up a quantum computer? The general purpose here is to encode parts of the problem into a complex quantum state using qubits, and then modify the state to move it towards something that will ultimately represent a solution that can be calculated after the superpositions have collapsed into deterministic sequences of zeros and ones. As in classical programming, scientists are also trying to shift low-level assembly languages that the computer best understands to high-level languages and graphical interfaces that are more suitable to the human mind. For example, IBM's Quiz Kit lets experimenters set up problems and drag-and-drop logistic gates. The devil in decoherence. Then why aren't quantum computers more common? In a way, physicists are attempting to make ideal devices out of imperfect bits. Quantum computers are highly susceptible to disruptions, noise, and other external factors that cause their quantum state to waver and vanish, an effect called decoherence. For example, for certain researchers, decoherence is a problem that pushes up quantum computation. Even with the best caution, noise will sneak into the calculations. Scientists can only hold quantum knowledge for as long as they sacrifice their fidelity, which reduces the number of measurements that can be done in a row before anything collapses. The fragile nature of quantum computing is also why blindly adding qubits to devices does not actually make it more efficient. Fault tolerance is a heated research field of quantum computing. Technically, adding qubits could compensate for some of the issues, but millions of error-correcting qubits that are probably needed to construct a single, stable, data-carrying qubit, today we're at about 128. Smart algorithms, though still in their infancy, could help as well. Since big data is all the rage, you would expect quantum computers to manage larger databases better than traditional ones. Quantum computers are extremely effective at stimulating nature. For example, in drug creation quantum computation, drug molecules may be constructed more effectively because they actually work on the same basis as the molecules they are attempting to stimulate. Computing the quantum state of a molecule is extremely computationally difficult for our modern processors, but it's right up the quantum computer's alley. Similarly, quantum computations may also revolutionize the science of materials or the transfer of knowledge. Thanks to entanglement, qubits physically isolated by long distances could theoretically create an information transfer channel that is clinically proven to be more reliable than our existing networks. Quantum internet is not a crazy imagination. But maybe the most thrilling thing is this: we don't even know all the exciting problems quantum computers can solve. Only by making a commercial quantum computer available and having people play with it, awesome engagement at a distance, we can be able to find other interesting fields that are well suited to this mind-blowing new technology. Would you like to get your hands on a quantum computer? What would you use it for? Let me know down in the comments below and check out some of these other videos. This has been Mr. Singularity, and I'll see you on the next one.